in a polycrystalline material, grain size is a very important parameter, since the mechanical properties of a polycrystalline material depends very much on the grain size. For example, the tensile strength and hardness of a polycrystalline material will continuously increase as the grain size becomes finer and finer. It is therefore very important to devise suitable methods by which grain sizes can be accurately measured. Now, in a normal polycrystalline material, we find that the average grain size varies between 10 to the power minus 2 to 10 to the minus 3 centimeter. Now, it is quite usual practice to describe the grain size of a polycrystalline material by mentioning what is known as the Astm grain size number. Now, let us see what is meant by the Astm grain size number. Astm, as we all know, stands for American Society for Testing of Materials. Now, they have given a formula written as small n equal to 2 to the power capital N minus 1, where small n is the number of grains per square inch at a magnification of 100, and capital N is the corresponding Astm grain size number. So, if as a routine matter it is necessary to find out the grain size of a polycrystalline material from time to time, one of the ways will be to take known grain size materials and find out pinhole photographs from them. Then from those pinhole photographs we determine what is the Astm grain size number. Then those pinhole photographs can be arranged as per the Astm grain size number, as has been shown here. This is for the Astm grain size number 1, this is for the Astm number 2, this is 3, this is 4. So, whenever we have an unknown material given to us and we develop the microstructure and also find out the pinhole photographs from them, and then try to match the pinhole photograph of the unknown with the pinhole photograph of known grain sizes. In this way, the grain size of a polycrystalline material can be expressed by the corresponding Astm grain size number. When the grain size varies between 10 to the power minus 3 to 10 to the power minus 4 centimeter, we find that the Debye rings become continuous. For example, here if we can see, the Debye rings are quite spotty. Here the Debye rings have not really formed yet. Here the Debye rings, we can see the outline of the Debye rings. Here the Debye rings are spotty. The reason is the grain size is large. In this case, it's a Debye ring is continuous, indicating that here we have a smaller grain size. So, as the grain size varies between 10 to the minus 3 to 10 to the minus 4 centimeter, the Debye rings become quite continuous. In fact, no change in the Debye rings is observed when the grain size varies between 10 to the minus 4 to 10 to the minus 5 centimeter. The moment the grain size becomes 10 to the minus 5 or less, there is a broadening of the dividings which is observed. So, this is a cutout value when the grain size is 1000 angstrom or less, the lines show a broadening behavior, and the individual grain size less than 1000 angstrom, we call those grains as particles. So, here we have a number of pinhole photographs. These are the 4 which I have already shown. So, here the particle size is 0.1 micron, and then it goes down, decreasing particle size. As you can see here, the dividings form exactly at the same locations, but the width of the dividings is somewhat more than in case of this. As the particle size decreases further, the width of the dividings becomes more and more. So, there is a perceptible line broadening which is observed when a particle, its size decreases further and further. Now, there has been a method that has been developed to measure the particle size from the broadening of the lines of the dividings. So, we will discuss that particular method. Now, when we have the Bragg law perfectly satisfied, then what we expect? We would expect that all the diffracted intensity will be concentrated at 2 theta b, where theta b is the Bragg angle. So, this should be the shape of the diffraction line profile for when Bragg's law is perfectly satisfied. But what we observe in practice? In practice, we find a diffraction line has this kind of a profile. So, it has a measurable breadth at half the maximum intensity. So, whenever we have a line profile, we measure the breadth of the line profile at half the maximum intensity. So, this is the maximum intensity for the line, and this is half the maximum intensity level, and the breadth here is the line breadth b. So, what we observe that this kind of a behavior is found for incident angles slightly larger than the Bragg angle, and also for slightly lower angle than the Bragg angle. Beyond that, there is a practically no intensity obtained. So, this line profile shows that even when Bragg's law is not perfectly satisfied, we will find some intensity. So, this is the non-ideal Bragg condition, and the reason is very simple. You see, whenever we have diffraction occurring from a series of planes, say when the incident in radiation is theta b, the Bragg angle necessary for diffraction, then there will be a diffracted intensity. But even when the Bragg's law is not perfectly satisfied, that means the angle, the incident angle is slightly different from theta b, then also we find some intensity. The reason is very simple. In order that complete destructive interference to take place, we need that the diffracted wavelengths will be completely out of phase. If at these 2 points the diffracted radiations like x0 and x1, if they are completely out of phase, then only there won't be any diffraction. But say for example, if by some chance we find that they are not completely out of phase, even then there will be some diffracted intensity. Its intensity will be much less as compared to when the Bragg's law is perfectly satisfied. So, this is a very important observation, that even when Bragg's law is not perfectly satisfied and when the incident angle of the X radiation is slightly more or slightly less than theta b, even then we will get some intensity, as a result of which an actual diffraction line profile looks like this. So, this is practically the cut off angles beyond which there won't be any diffraction possible. Now, say for example, in this particular case we have got the Bragg equation satisfied when the incident radiation falls at the correct angle theta b. Okay. So, this is the d value, the interplanar distance. So, let us suppose that when the incident X rays are incident on these parallel set of planes at the correct Bragg angle, then x 0 and x 1 they constructively interfere totally and giving rise to the Bragg's diffraction. Bragg's law is perfectly satisfied. Let us suppose that when theta is theta b, the correct Bragg angle, the path difference between the rays x 0 and x 1 is equal to 1 wavelength lambda. Now, if we consider a crystal containing a series of these planes right from plane 0 up to say plane n, then what will happen? What will be the path difference between the ray x 0 and x n when Bragg's law is perfectly satisfied? It will be n times lambda. Now, suppose we increase the angle of incidence of the X rays to a value theta 1. So, theta 1 is slightly larger than theta b. So, in this case what we find? In this case the path difference when theta is theta 1 between the two rays will be slightly more than the path difference between the same rays when the perfect Bragg law is satisfied. So, in this case when theta is equal to theta 1 slightly bigger than theta b, the path difference between x 0 and x 1 will no longer be 1 wavelength, but plus delta lambda wavelength. And what will happen when the path difference between x 0 and x n under the condition when theta is theta 1 slightly larger than theta b? It will be n lambda plus 1 more lambda, it will be n plus 1 lambda. Now, why this is so? The reason is very simple. You see, if the path difference between the ray x 0 from the 0th plane and the x n from the nth plane is say n plus 1 lambda, then we must, it is very easy to visualize that within the crystal somewhere in the middle there will be a plane. The path difference between the rays from the 0th plane and the middle plane must be equal to lambda by 2, half lambda. You see that due to the increase in the incident angle from theta b to theta 1, there will be an increase in the path difference values. So, if for Bragg angle, when Bragg law is satisfied completely, if the path difference between the rays x 0 from the 0th plane and x n, the ray from the nth plane is n times lambda, then under this condition when we go up to a theta equal to theta 1 slightly more than theta b, but beyond which there is no diffraction possible, then the path difference between those two rays will be 1 lambda extra than this. So, it is n plus 1 lambda. Why this is so? The reason is, as I have already said, in the whole crystal here, this is suppose the whole crystal, and within this crystal there must be a plane somewhere in the middle which will be such that the path difference between x0 and the diffracted radiation from that middle plane must be equal to lambda by 2. As a result, what will happen? The radiation scattered from the 0th plane and the plane somewhere in the middle, they will nullify each other, they will be completely out of phase. In this way, if we consider the radiation, the scattered radiation from plane number 1 and the scattered radiation from the plane next to the middle, they will also nullify each other. So, in this way, in the top half of the crystal, the planes in the top half of the crystal, the radiation scattered from them will be nullifying the radiation scattered by the bottom half of the crystal, as a result of which we will find there will be no diffracted radiation possible beyond the value of theta 1, and that is what we are observing here. In a similar way, if we decrease the angle of incidence from theta b to say theta 2, where theta 2 is just slightly away from theta b, then we will have a similar situation that the path difference between x0 and xn will again be equal to n minus 1 lambda, because here the path difference will be shorter. When theta 1 is larger than theta b, then the path difference between the two rays will be somewhat larger as compared to when it is theta b. And again, when it is theta 2, where theta 2 is less than theta b, it can be shown that the path difference between the rays will be somewhat lower than in case of when the Bragg's law is perfectly satisfied. So, only in these conditions we will see that beyond a value of theta 1 or beyond a value of theta 2 for the incident radiation, there won't be any more intensity, and as a result of which the line profile will have a shape of this type. So, this is what I have already explained. So, this is say the outline of the crystal we are considering, and there are planes marked as 0, 1, 2, 3, 4 etc. up to n. So, the thickness of the crystal T we can write as n into d, where d is the interplanar distance. So, this is the situation, T is equal to n into d. Now, when perfect Bragg law is satisfied for this particular crystal, we can write down 2t sin theta b must be equal to n times lambda. Well, between two consecutive planes, it is 2d sin theta b is equal to lambda. So, for the whole crystal, it will be, when you consider the radiations from the 0th plane emanating from 0th plane and the nth plane, we can write down when theta is equal to theta b, 2t sin theta b must be equal to n lambda. And when theta is theta 1, where theta 1 is slightly larger than theta b, the corresponding equation will be 2t sin theta 1 equal to n plus 1 times lambda. When theta is theta 2, where theta 2 is slightly smaller than theta b, we find it can be, the whole equation can be written as 2t sin theta 2 is equal to n minus 1 lambda. This is clear from what I have said already. Now, if we subtract equation 3 from equation 2, we can write t sin theta 1 minus sin theta 2 will be equal to lambda, or 2t cosine theta 1 plus theta 2 by 2 sin theta 1 minus theta 2 by 2 equal to lambda. Now, you see theta 1 and theta 2, they are not very different from theta b. As we know, when we talk about a diffraction line profile, it is true that the intensity is obtained not only at exact 2 theta b, but also beyond 2 theta b in both the directions, but it is available only up to a certain angle. You know, I have shown it on a much magnified scale, but you know the angular range within which we get reasonable amount of intensity will be very, very small. So, you see that theta 1 and theta 2 are not much different from theta b, and so each one of them can be written as almost equal to theta b. So, in that case theta 1 plus theta 2 becomes very close to 2 theta b, and sin theta 1 minus theta 2 by 2 can be written as simply theta 1 minus theta 2 by 2, because this difference is very, very small. Now, from this triangle, by similar triangle concept, we can write b, this width of the line here, divided by 2 theta 1 minus 2 theta 2 is equal to half I max by the entire I max. You know, here it has been written the other way around, there is a mistake here. So, it will be b by 2 theta 1 minus 2 theta 2 will be half I max divided by I max, that means it is equal to half. So, we write b by 2 theta 1 minus 2 theta 2 is equal to half I max by I max, or it is simply equal to half. Or we can write b by theta 1 minus theta 2 will be equal to 1, or b is equal to theta 1 minus theta 2, very important relationship. Now, equation 5 now can be rewritten in this form, you know, because of these values. If we put those values there in equation 5, you can write it as 2t cosine theta b into theta 1 minus theta 2 by 2 equal to lambda. 2 and 2 will cross out, and we will get t cosine theta b into b becomes equal to lambda, or t is equal to lambda by b cosine theta b. This is a very important relationship. You know, t, the thickness of the crystal, or we can call it the particle size of the crystal, is equal to the lambda, the wavelength that we have used for taking the pinhole photograph or the Debye photograph. It is divided by b, the breadth of the line at half the maximum intensity, multiplied by cosine of the Bragg angle. Now, more rigorous exercise yields a more exact value, and that is t is equal to 0.9 lambda by b cosine theta b. This is the well known Scherrer equation. So, you see that by using the Scherrer equation and by measuring the line breadth and the value of cosine theta b, where theta b is the Bragg angle, it is possible to find out the size of the particle. So, this is how particle size is determined by the X-ray diffraction method. So, this is the situation. If this is the breadth of the line profile, we can find out t is equal to 0.9 lambda by b cosine theta b. This is the well known Scherrer equation. Now, if we use a diffractometer, then in a diffractometer output will give the lines in this shape, and from there you can find out the line breadths straight away and use in that equation. Now, you see, when we talk about the breadth of a line, how to measure the breadth of a line? Actually, there are several ways it can be done, but we use mostly the method given by Warren. You see, whenever we use a Debye camera or a diffractometer to find out the line profile of a diffraction line, there is always some instrumental broadening. For example, in case of the Debye method, it is because of the divergence of the incident radiation, due to which there will be some broadening of the diffraction lines. And in case of a diffractometer, again it is because of the size of the X-ray spot which causes some broadening of the diffraction line. So, these are called instrumental broadening, broadening due to the instrument itself. So, the total width of a line, total breadth of a line, it is a function of two things. One is the particle size, the other is the instrumental broadening. So, whenever we want to measure the breadth of a line, in order to find out the particle size, we have to be careful to consider only that part of the broadening which is due to particle size alone. Now, how to determine that? Now, there is a method which was suggested by Warren. So, what is Warren's method? He has suggested that he has suggested a formula where B square is equal to B T square minus B S square. So, what is B square? B square is the square of the broadening due to particle size alone, and B T square is the square of the total broadening measured from the diffraction line profile, and this broadening is due to the instrumental broadening. So, square of the broadening due to the instrument. So, Warren suggested that we determine B from this kind of an equation. This kind of an equation is suggested on the idea that the diffraction line profiles look like error curves. So, that is the reason why this kind of relationship was suggested by him. Now, how to find out the value of Bs, because Bt is the total measured breadth, and what is Bs, how we find out the value of Bs? Well, we can do it in this manner. The material which we are working on, we mix a standard material with it, and the standard material must have a particle size greater than 1000 angstrom. So, in that case what will happen? The standard material, if we get a diffraction line, the breadth of the line will be due to the instrumental broadening alone, not for particle size. So, what we do? We mix a standard material with a particle size which is larger than 1000 angstrom, so that any line, the diffraction line from the standard, will not show any breadth due to particle size only, and it will show only the instrumental broadening. Then we mix the two and take a diffraction pattern, and we choose a line from the experimental material and the standard which are close by, and in that case what we will do? We will simply measure the breadth of the standard line, square it and subtract it from the square of the measured breadth, and from there we can find out B square, and so we can find out B. So, this is the way we can find out the breadth of a diffraction line due to particle size alone. Now, it may so happen that we may have a polycrystalline material containing very fine grains, they are of the size of particles. The problem over there is, in such materials it is quite likely that there will be some non-uniform strain throughout the material. So, if we measure the diffraction line profile, the breadth will also, some of the breadth will be due to the strain also, there will be some strain broadening. Therefore, this method that we have described is not suitable for determining the fine particle size in polycrystalline sheet materials. It is good only for material where the powder is in a loose condition and there is no strain in the particles. Now, so far as application of this method is concerned, industrially this method is used for measuring particle size of carbon black, industrial dust, etc., etc.